So I would just like to give you a feeling about the concentrations of these vacancies, just to convince you that these are not negligible numbers. They can be actually real and measurable. Excuse me. We will go through an example of copper at 1,000 degrees, and we will consider 1 cubic meter of copper. So the question is, how many vacancies do you have, and what is the concentration of the vacancies in this material? So we know that the magnitude of K is 1.38 times 10 to the minus 23 joules over Kelvin, because the activation energy is typically expressed in electron volts. So you have to convert this into electron volts. So this is 8.625 times 10 to the minus 5 electron volts per Kelvin. So you need to know the molar mass of the material that you're considering. So you first calculate the number of the atoms in that particular volume. So this will be simply an Avogadro number times the density times the volume, which we know, over the molar mass of the material. And when you plug in for the values for copper at 1,000 degrees, you know the density, you know the Avogadro number. You will it turns out that there are 0.8 times 10 to the 29 atoms in this particular cubic meter of copper. So you know how many atoms you have, and you can calculate the concentration or the number of the vacancies using this equation. So because I'm here writing the concentration of the vacancies simply because number of the vacancies is usually much, much smaller than the number of the atoms. So this can be represented as small n over large n, or the number of the vacancies over the number of the atoms. So I can calculate the number of the vacancies, which will be 2.2 times 10 to the 25 vacancies, again, per cubic meter. And when you calculate the concentration, this will be, in this particular case, be 2.75 10 to the minus 5. So simply by knowing what is the activation energy for the formation of the vacancies in this particular material, you can calculate what is the equilibrium concentration of the vacancies at a given temperature. So in turn, if you, for example, have a given material, if you can calculate the concentration of the vacancies, then you can calculate what is the activation energy. Okay, so with this, I would just also like to give you a couple of examples. So these are the examples of the equilibrium concentrations of the vacancies for two activation energies. And the reason why I'm showing them is just to demonstrate that these are the typical numbers. And at the same time, for a given temperature, the concentration of the equilibrium concentration of the vacancies can be dramatically different. I'm changing the activation energy by 4 times, so from 0.5 to 2 electron volts. And you can see that the concentration of the vacancies is changing by 15 orders of magnitude. So there are dramatic changes, right? At the same time, if you simply change the temperature just by a little bit, then the equilibrium concentration again can change dramatically. Simply from going from 500 Kelvin to 1,000 Kelvin, you're changing the concentration by 10 orders of magnitude, okay? Or even more than that. So the other thing that I would like to point out is that these numbers can be really significant, right? So this comes to, you can measure the vacancy concentrations in the ranges of percentages. So if I told you that you have a material and you should estimate the concentration of the vacancies, it's not really intuitive to say that you have a concentration of the vacancies in the range of percents, right? But there are situations where that can happen, okay? So these are real numbers, they can be calculated, and etc. So the next question is then, how do you measure them, right? So if you have a point defect, and if I told you, calculate the concentration of the point defects, how would you do that? Measure. So I'm giving you a piece of a material, give me and measure the concentration of the vacancies. What would you do? Can you use any of the techniques that we mentioned? Yes?
Can you compare the theoretical and measured densities?
Density. Okay. Good Good guess. Okay. Do you think that these numbers are measurable, that these differences are measurable? Usually they're very small. So the density measurement is a good guess. You do change the density, but it's usually almost negligible. Okay? Can you use diffraction? So if you have a piece of a material, right, and you take a diffraction pattern of it, and then you introduce point defects in any possible way, would you expect that the diffraction pattern changes dramatically? The answer is probably not, because the concentrations, you're just taking away certain relatively small percentage of the atoms, right? We mentioned that the concentration can be significant, but usually it is relatively small in comparison to the number of the atoms. So the strain and the change in the atomic positions that would influence the diffraction are actually relatively small. So the diffraction patterns usually cannot be used for this purpose. So the reason why I'm asking you this is just to show you that there are a set of experimental measurements that actually enable people to calculate and measure the concentration of the point defects. And one of the very first ones was in 1960 that is somehow similar to the density measurement, but what was actually done in that particular case is that they measured a length or the change in the length of a piece of a material, and I apologize, I don't remember what was the material. It was aluminum. Okay, so what they basically measured is the length of a bar of aluminum. And if you know what is the thermal coefficient of the thermal expansion of the aluminum, you can predict how the length of the material will change if you simply assume that thermal expansion. And they realized that this number is different from what we would calculate. So the measured and the calculated numbers were different. And the reason for that is that if you simply have a thermal expansion, the atoms would simply, so the material simply expands. But if you start to introduce vacancies, then some of the atoms leave the material and end up at the surface, and then they contribute to the extension or to the expansion of the material also as a function of the temperature. So what they did is that they simply calculated what is the change in the length of the material total that has two components. One was due to the thermal expansion, and the other was due to the change or the change in the concentration of the vacancies. So we mentioned that this is a temperature-dependent property. So when they measured this, so for the case of aluminum, so this is what they obtained. So this graph here shows the change of the length of aluminum bar as a function of temperature. So the solid line would be the measured, and the dashed line here would be the line that was predicted simply by taking into account the thermal expansion. And the difference, this tiny difference between these two curves, so this tiny difference here will give you the concentration or the expansion that is due to the presence of the vacancies. Okay? So you can see that these two graphs are very, very similar at low temperatures, and then they open up. And this difference becomes more and more significant at higher temperatures. Why does it become more significant at higher temperatures? Why these two graphs are more apart at higher temperatures? Hey guys, are you sleepy? You are? Okay. So, 10 more minutes. So why these two graphs? So first of all, we mentioned that they're separating, right? Why the separation is greater at higher temperatures? Yes?
Are there more vacancies at higher temperatures?
Is that a question or a statement?
Okay.
So, are there more vacancies at higher temperatures? Yes, okay. So, But, okay, so we just learned that this is a thermally activated process, right? So at higher temperatures, there is more vacancies. So therefore, the number of the atoms that are contributing to the extension simply due to that is greater, okay? So just checking if you're following. Okay, so luckily, as the experimental measurements have progressed, now we have direct experiments that help us to directly visualize these things. And what this particular image or set of images shows you, this is the surface of a nickel aluminum alloy. And what you see on the surface are circles. So these circles are single atom layer islands. What that means is that you have a flat surface of the material, but on the surface itself, there are atomically thick layers of the atoms. And in this particular image, they're represented as circles. So this is just the border of one island, and then these other circles around are just individual islands that grow out of it. So this particular set of images here shows you how these circles look like at different temperatures. So if you go from this image here, and then you move this way and then this way, the temperature is increasing. And what you can see is that the radius of an individual island grows, right? So you see this starting island here, then it grows, and then eventually ends up in a huge island here. And what that means is that the island is growing because the number of the surface atoms is increasing. So you're forming more and more vacancies, and they are diffusing to the surface of the atom, and this island here grows and grows and grows. So again, this was in 2001, and again, this was a really, really beautiful paper because it was a direct visual information about the formation of the point defects. And since 2001, luckily the techniques in material science have progressed to the level where we can see directly the presence of individual point defects. So here I'm showing you really state-of-the-art microscopy work where you can see individual point defects. And in this particular case, this is a case of graphene. So these individual dots in this image here are carbon atoms. And at a certain temperatures, you start to form these defects that are indicated as in these borders here. So this would be an individual carbon vacancy atom, and it shows up as a contrast in this image. So again, the reason I'm showing you this is just to show you that the experimental techniques in material science have really progressed since 10 years ago. Now we have the ability to directly see these things and measure them and understand them in more detail.